Greetings, everybody. This is my tape class for April 8, 2008. In this tape class, I'll describe the new instructions in Vesp 3.0. These instructions are also used in Vesp 3.0K, which is the kernel version of Vesp 3.0. What I will primarily do in this tape class will be to highlight the changes in Vesp 3.0 in contrast to Vesp 2.0. The primary changes are in those instructions that we felt a little bit too short or too congested in terms of the functionality or the functionalities they provided to us. One of those instructions, if you recall, was an add instruction where the result of the addition would have gone into register A. So in this extended 3.0 version of Vesp, we will be able to compute the addition of A plus B and store that into register B. We will also be able to do subtractions in a more straightforward fashion than we were able to do it in the case of Vesp 2.0. So what you see here is that these instructions have been extended by tapping their hexadecimal code space. In the case of the addition, we simply think of the addition as in the original format as 0, 0, and if we were to add some more addition operations, we would then extend as 0, 0 to 0, 1, 0, 2, 0, 3, etc. So that's for the add instruction. Now, in this particular case, I have left alone the complement instruction, even though we could have as easily enhanced the complement instruction and provided for a complementation of register B as well as register IX. The load and move instructions are somewhat more difficult to handle because we do use the address fields of those two instructions, and because of that they are somewhat more difficult to extend. So I left those two instructions alone. Likewise, jump instruction, the jump if 0 and jump if positive instruction, all of these three instructions use an address portion in the instruction word. As a result of that, I left them alone. As you could see that I have not extended them here, and so they have not been modified. Now, we will end up generating some additional jump instructions in order to facilitate some other conditional jumps, but they will be done via the halt instruction, and that will provide us some extra coding space. As you recall, halt instruction doesn't really take any operands. One of the limitations of these jump instructions, as we shall see later on, will be that the address field for the jump instruction that we have in question will have to come from another place, and in this case I've actually elected to use register B to make that address field specifiable. The increment and the decrement instructions have both been extended to include the incrementation of A and B, the B register. That we will see later on. And the same applies to the end, and then the OR, and then the shift, and then the shift left and the shift right instructions here. Again, as in the case of load and move instructions, I have left MXF and MXT instructions alone because they both use the address field in instruction words. Now, this is the original set. Excuse me. This is the original set of Vesp 2.0, and so when we extend these instructions, we will have the new instructions that are added in Vesp 3.0, which they come on the next slide. Excuse me for one more time. So as you see here on this next slide, I have, for example, taken the first opcode, which was all 0, and we were not using the hexadecimal digits past the first one in the case of all of the other versions, previous versions of Vesp computer, and I have now added instructions such as add A to B, add A to X, subtract B, subtract A, and subtract IX. And these have been given new opcodes with 0, 0 remaining as, in fact, the original add instruction we had. So you can see that in the case of add B, the result of the addition goes into register B instead of A. If I say add X, then the result of the addition goes into IX. And likewise, in the case of, we actually did not have a subtraction instruction in the other versions, earlier versions of Vesp, but here we have a subtraction instruction which takes A minus B and puts it into A, and that could also be moved into B, which is the SUA instruction, and even put into IX, which in this case is going to be SUX instruction. So we've effectively added 1, 2, 3, 4, 5 new instructions, all of which are doing simple additions or subtractions, which we did not have in the previous versions. As I mentioned earlier, the jump instructions have been extended considerably, but at the expense of having to specify a branch, a potential jump address over here, and that will have to come from another place because we cannot have the address space any longer as we are actually using it to specify these instructions. So the original instruction of 7.0, which was our halt instruction, has now been extended into 7 more instructions by simply adding or picking up the next hexadecimal digit in that 4 hexadecimal digit instruction format we have. And each of these has been given an interpretation. For example, this is jump if A is equal to 0, jump if A is greater than 0, which neither of which we had in the previous versions of Vesp, jump if in fact A is negative, or jump if A is greater than or equal to 0, jump if A is less than or equal to 0, that's minus or 0, and jump if A is not equal to 0. Those are the new instructions, conditional branch instructions, which I've added here and given them a new hexadecimal codes. Now, of course, I also added something called no operation, which is sometimes used to fill certain instruction spaces in programs, but they're also used in commercial machines to allow effective pipelining in the case of what we call branch prediction schemes. That you will learn in ENEE350-Week-10. So these are our new jump instructions then, and then I've also modified the incrementation and decrementation instructions. As you can see, I have here increment B and decrement B, and increment X and decrement X instructions, which we did not have in the earlier editions or versions of Vesp. Now, these are then the corresponding and then the OR instructions, which I've limited to register B as opposed to including IX as well. And then we have shift left and shift right instructions as well. Now, in this case, for the B register, not just the A register, as we had in the past. So these are the new instructions that I've added, with which now we can do actually more powerful computations. And so on the next slide, I'm going to sort of show you how, in fact, I've incorporated these into the flow of the new Vesp. And as you recall, we had really 2 compartments here, one of which was the decoding process and the other one of which was the execution. So I'm just simply showing you here how the new syntax has been introduced into the decoding process. As you can see, in the case of 0x0, that's hexadecimal 0, I'm not only looking at the leftmost hexadecimal digit, which this would have given me, but I'm further decoding, as you can see here. This is somewhat redundant here, but I just wanted to make sure that I only pick up the rightmost 4 bits to get my second hex digit after having shifted it 8 places. And this gives me then the possible extensions of the add instruction, which in fact it could have gone up to 16, and I've just limited them to 1, 2, 3, 4, 5, 6 such instructions. These are basically, as I told you on the earlier slide. So this is just the decoding process, which simply gets us the printout of ADA, ADB, ADX, and so on. As in fact we're decoding instructions, these will be displayed in the new version of Vesp. This is the 3.0 version. And the complement remains as it was before. Load is the same, move is the same, jump is the same, and so on. These have not been really touched or changed, but in the next group, which is the halt instruction, as you can see, I one more time am looking at the rightmost 4 bits here, which is in fact the second chunk, having shifted it 8 places to the right. I'm now looking at the rightmost bit, rightmost 4 bits, which is the second hex digit, to see how I should interpret the so-called the instruction group that begins with a hexadecimal digit of 7, which is here. So, and the interpretations are already committed on the very first slide, or the second slide we had, or the third maybe, where we clearly delineated these instructions as the new instructions in the sort of jump or the conditional branch category. In the next group here, I'm actually incrementing A, B, or IX, and those incrementations have been added in the next group, which is the hexadecimal digit of 8 on the leftmost side, and then after that I'm looking at the next hexadecimal digit rather, which is then done through this switch statement, and based on the value of that I could be doing either INA, which is increment A, or increment B, or increment IX. And so this continues on to the next group, which will be the decrementation instructions, decrement instructions, which are then done here. And the add instruction is only going to affect A and the B registers, but not the index register, and the same is true for OR instruction. As you can see that this time we're looking at A and B hexadecimal digits respectively for AND and OR on the leftmost side, but then we have to further interrogate the next 4 bits, which will give us the breakdown of that group of instructions into further instructions here. Like here it's A equals A or B, or B is equal to A or B. Shift left and shift right instructions are done the same way, and then move from with index and the move to with index instructions have been left alone again because they have the address space, which we cannot modify in this case or use to extend them into new instructions. This next slide shows us what happens in the change or in the new version of Vesp so far as the execution process is concerned. So now we're looking at the execution process, not just the decoding alone. And as you can see, having looked at the leftmost 4 bits, which is the first hex digit, and seeing that to be 0, 0, we are now going to look to see how that first hexadecimal digit of 0 will further be decomposed or decoded by looking at the next hexadecimal digit. And so and then again, the way we did it before in the decoding process, we're looking at the second hexadecimal digit, which this operation or this switch statement does here, and then we could either have 0, in which case we do the regular A plus B, and the rest of the code is exactly how it was in Vesp 2.0, or we do B equals A plus B, in which case we're actually writing the result not into A as we did over here, but into B, and you can see that that happens here. B is equal to temp as opposed to A is equal to temp here. So I guess in the next one we will put the temp, which is the sum of A plus IX, into the IX register, and so this should have been actually IX equals IX plus A, not B. So let me just quickly fix it and come back here. Let me just do that right there. This is a wrong comment I inserted in there. So we're back on this same instruction, but it's IX plus A. So that's what really goes into the IX register in the end. And then the one after that is A equals A minus B. This time we're actually using the complementation operation in order to be able to do this subtraction. And that will then be brought back into this register A. So as you can see that the temp, which is A minus B, now goes into A, which effectively is the subtraction of B from A being stored back in A. Okay, and you could do B equals B minus A, in which case we do B minus A and put that into B. Or you could do IX, again, I think there's something wrong here, which I'll fix very quickly. This is supposed to be A here, and once I put that in there, let me just do it this way, then we have it corrected. And we put now IX minus A into IX, and that is done right down here. So once we put it into temp then goes back into IX. Okay. In between, we check all kinds of overflow issues, but that I think is the same as before in other versions, early versions of Vesp 2.0. So that was the group of arithmetic instructions we incorporated into Vesp 3.0. These are now the conditional jump instructions. Again, we look at the rightmost, the second rather, most significant hexadecimal digit, as you can see here, and if that were to be 0, that's our original halt instruction, so which is now really not 7 any longer, but 7-0 as an opcode. And then we extend that into further conditional jump instructions, like this one here is basically a conditional jump instruction which simply makes makes Vesp rather to jump into the address which is stored in register B here, as you can see. Now again, I've noticed that I've made a small mistake here, which I will actually change. If I've coded these the right way, this should really be equal to 0, and this should be less than or greater than 0. And if that maintains the order in which I define these instructions, then they will actually be defined the same way as we went over them in the decode operation. And so you could pretty much follow the rest of it. You know, A is equal to 0, A greater than 0, A less than 0. I think the key thing to notice here is that in each of these cases, we can no longer pick up the address from the instruction because we've already used the 2 hexadecimal digits. So what we really have left, and that could have been an option, only the rightmost 8 bits of the instruction, and we could then have incorporated that into the address space, or the branch instruction with an address specified in the instruction itself, and left alone register B. But that would only give us a 256 locations to branch to, because with 8 bits that's the largest address you can specify. So rather than doing that, I opted to use register B, which could restrict the utility of these instructions unless you really save register B into some other place if you're using it in your computations prior to loading an address in there to prepare for a possible branch on the outcome of a condition you're testing. So that is maybe one limitation, but not too big an issue. It still allows you to branch with these new conditions, albeit at the expense of having to store B, the current value of B somewhere, and load an address into it just in the case that you end up branching to someplace. So that was just that. And increment and decrement instructions are similarly extended. As you can see, this is the increment instruction where we're incrementing A, and then we're going to put that back into A, or we're incrementing B, as we do it right down here, and putting it back into B. So this is just the incrementation. The extension, again, we always do it by looking at the second hex digit here. Increment IX is the third possibility in this case. That's one of the new increment instructions, and you can see that increment IX goes into temp, and then temp goes into IX. Okay. Now, the same applies to decrement, so I'm not going to labor about this too much. The same operation, the same computation. Instead of incrementing, we're just decrementing, and that's just like evident in the process. Here's A minus 1, here's B minus 1, and on the next slide it will be just IX minus 1, which then goes back into IX. So there are three new instructions here. Actually, two new instructions. The IX, we're able to decrement it now. We're also able to decrement the B register. The AND instruction, the same way. We have a possibility of now ending A and B and putting it into A, or we have A and B put into B. So that's our new instruction. Again, that happens assuming that we've initially decoded the first hex digit to be A. Now we could have A0, which in this case we'll do A and B put into A, or it could be A1, which we then interpret as having A and B put into B. And there's an OR instruction, which is pretty much the same. Instead of AND, we're now doing an OR version of the same. Now these instructions can be extended, so you can actually take A or IX and put it into A, and in the same way the IX versus AND instruction. But there is enough space here to be able to do that, because with the next hex digit we've only tapped 2 out of 16 possible opcodes that we could really have, and so there's plenty to expand this machine into a lot more instructions that I've done, but these are the ones that will prove to be handy in the case of kernel operations that we've been discussing. The shift left the same way. We have now the ability to shift A to left by 1 or B to left by 1, as you can see it here. And so the extension in this case is just primarily to include the shift on B, not just A. And I guess I just went back, so if I go forward, that will be shift right, and this is the same as shift left. Now, except that we included again B as a possible target of the shift, source and the target, of course, not just the target, but the source and the target of shift. So we shift B by 1 bit to the right and then put it back in B. Now, I want to talk a little bit about the MXF and the MXT instructions insofar as their modifications go for Vesp3.0K. Now, MXF and MXT instructions are not really modified or have not been modified in Vesp3.0 per se, but they are modified or they have been modified in Vesp3.0K for kernel. And the difference is in the kernel version we're somewhat more cognizant or conscious of the potential ills or the potential problems that may be generated by writing into undesirable memory locations in Vesp kernel. So I have put in some minimal protection, as you will see in just a second here, on MXF and MXT instructions, which you should, I think, understand, because as you write kernel code, in the next homework, for example, you really have to make sure that those instructions that you include in your programs do not inadvertently write into places where you actually have the kernel or the bootstrap code resides. So what is really happening here, if we just go over this very slowly, this is our good old MXF instruction, but we're making some checks here, and the checks are intended to avoid writing into places which are not desirable. And in this case, it's a minimal restriction. You can really enhance this both in this sort of instruction level or in the kernel level, where as you write your kernel code, you may not allow programs to write into locations that may possibly modify code. That you can always do by trapping those instructions that make references to memory, and if they do, you just simply check to see if they are properly referring to memory locations. Now, so here's what we do in this case, in this minor modification that I've done. We simply check to see what is contained in what's called a virtual address register, which this is. So what we do, we look at the so-called, this is actually a 4-bit register, but the way things are defined in C, when I define it as, I guess, short integer, it's going to be 16 bits. So I'm basically looking at the leftmost hexadecimal digit here, if you like. And that I'm just checking to see if it's equal to 0 or if it's equal to 1 here. So those are the two cases that I'm really considering. And in either one of these cases, I'm going to check to see where the value or the address in the IX register comes from. It could come from either the physical memory of Vesp, which is Vesp.memory here, or it could actually come from the hard disk, which is Vesp.hard disk. So what I'm really doing here is I'm using the 16-bit address in IX as the source of my move instruction, and in the case that that IX instruction has a 0 hexadecimal digit on the leftmost side, I am then limited to the first 12 bits of address space, and then I'm just using the so-called the physical memory space of Vesp to pick up the whatever it is that I want to move from memory into another location in the same memory. So if the leftmost digit, the hexadecimal digit, turns out to be 0, I know that that particular operand must come from the physical memory, the Vesp.memory, and that's what I do use to load into the MDR register. If on the other hand it's not equal to 0, it must actually come from someplace which is outside of the physical memory of Vesp. And so I'm only allowing myself in this implementation, if you like, to have that operand to come from the next page, which is basically the next 2048 locations, if you like. And in that case, I'm just simply loading that operand from the hard disk. So I could potentially make this equal to greater than or equal to 1, and then pick it up from anywhere in the hard disk. Maybe just avoid the bootstrap code, which is, if you recall, which was located in the topmost 256 locations, and outside of that, I could simply move everything into MDR without any problems. But in this case, in the simple case, I'm only allowing myself to actually to have an operand to come from the next group of 2048 locations. Otherwise, I will simply declare a page fault and not execute the instruction. Okay, so this is as if that I only have really two pages of 2048 words. The page which includes a hexadecimal address or digit of 0 or a hexadecimal digit of 1. Those are the two, and then the remaining 12 bits obviously will give me 2048 locations. I think I've been saying that wrong all this time, because obviously with 12 bits I'm able to go to 4096 locations, not 2048. Okay, so let me just stand corrected on that one. I've been meaning to say 4096 locations. Okay, so because we got 16 such blocks of memory once we isolate the leftmost hexadecimal digit. So to recap all of this, what we're really doing here is checking to see if IX has an address which either belongs to the first 4096 locations or the next 4096 locations. In the first case, we assume that the operand is in the physical memory of Vesp. In the next case, it is in the hard disk space, which is not all of the hard disk, but in this situation I'm only using the next 4096 locations, and then we copy that into MDR. If I don't find that address to be either in the first 4096 or in the second 4096, I'm, in this case, in this implementation at least, I'm declaring this to be a page fault. Okay, and if I don't really have a page fault, I would then have to, I guess I should probably exit out here, which I haven't done in the case of a fault. So in the likelihood that I have a page fault, I should just bail out of here. As I just write down here, it would be a place to call a trap and exit to the OS, but I haven't quite done that. But if I just ended up having the address either in the first 4096 locations or the next 4096 locations, I would then take that very operand, which I have put into MDR, and then copy it, as you can see it here, into that location whose address is given in the instruction, which in fact I have copied here into the MAR register. So I've taken the address portion of the MXF instruction, the 12 bits of it, and I then put it into MAR. I'm now copying whatever I found in the source, whatever operand I found, and put that into the location that is pointed by the address in the so-called 12 bits of IR. So you can see that in this implementation of MFX, we're only able to go to the first 4096 locations in Vesp memory, which obviously here is the physical memory, not the hard disk memory. So this instruction as such does not allow us to copy between hard disk locations, but only from a potentially hard disk location to a physical memory location, let's call it RAM location, or from a RAM location into a RAM location, okay, in this sort of situation, in the first part of it. Now, in the case that what we found, the address that we really tested over here to be not equal to 0 but 1, you can see that I pick up the address from the IX register, and instead of actually picking it up from the instruction itself, and then copying whatever I actually have in that IX register into the MDR register, not the IX register, but not the address register rather, but the location that is pointed to by that MAR register, and then put that into MDR, and then do the rest of the operation. And that's, again, assuming that in fact we're now in this page 1 as opposed to page 0, or if this so-called right-shifted MAR register happens to be 1, then I go ahead and then copy things from the hard disk. And of course the rest of it applies as before. We're still going to have to go to MAR from the instruction register's address field, and then but this time, as you notice, we copy things into the hard disk as opposed to the memory as we did over at the top. So the main difference between, I guess, this portion of the code and then this portion of the code, if you like, this versus this portion is that here the destination is the hard disk, whereas the destination down here or over here is in fact the physical or the RAM memory of Vesp. So the ultimate destination is adjusted depending upon what actually is stored in VAR. So we are, in the second case, able to move an operand from either the core or the RAM memory of Vesp into the hard disk space in the latter case. As you can see, that happens here. Whereas in the first case, which is this first portion, we're able to move something either from the hard disk, which is here, or memory, or the RAM or the core memory, into the RAM or core memory here. Okay, so that's the key difference between this portion of the code and this portion of the code. So I think having all of these things put together, then we have the ability to copy. Let's just emphasize that, to copy an operand, which is in the first 4096 locations of Vesp into either to those 4000, one of the 4096 locations, or the second group of 4096 locations of Vesp, or we could have taken it from the second group of 4096 locations and copy or move it to either the first 4096 or the second 4096 location. So I think effectively what we're saying is we can actually copy things as long as between any two locations, as long as they are within the first 8,192 locations of Vesp. But anything beyond will clearly give us what's called a page fault, so we have not incorporated in here the capability to copy anything which is outside of the first 8,192 locations. I think you can refine this code. Maybe I should just generate a homework problem out of this, so as to make this conditional move instruction to only exclude the last block of, I guess, 4,096 locations, and then allow otherwise the move with indexed register instruction to copy things up to that last block of locations. That could easily be done by just making some small changes in here. As opposed to saying equals 1, just make it greater or equal to, or less than or equal to 14, and just leave out the last page. I think that's a minor change. And so if none of those happen, then we just generate a page fault. Now, so the page fault can really happen in 3 different places here. As you just saw, here's one, okay, and that's because we are finding the source of the operand to come from a page outside of the first 2, or here the same way, or in the case that we are looking to copy things into some place, we find a place where we want to copy something to be outside of the first 8,192 locations. Each of those three cases can give you a potential page fault. This is now done at the instruction level. As I said, as you write kernel code, you can put additional constraints on users' programs to prevent them from inadvertently or maybe maliciously even into writing things or locations that you should not allow. The MXT instruction is the same, so I'm not going to go over it in as much detail, but it has the same structure, but the only change, as you can see, is in fact we're going to be looking at IX at the top as opposed to VAR. So if you just go back here, you can see that we began with Vesp3.0K, began to decode the instruction in this fashion, but this time, since we're actually going to a place which is whose address is pointed by IX as opposed to the source from which we would have gotten the operand, so at the outset here we begin with the interrogation of the address in IX. So that's the destination, which could either be in Vesp memory or it could actually be in Vesp hard disk, which is down here. And in each of those two cases then we have a potential the source to come from the hard disk or the physical memory. And so here's in the physical memory or the hard disk. And based on that we just act accordingly. So this is not a very complicated instruction either, but the key thing is that these page faults have been included in here so as to kind of prevent, I guess, Vesp from writing into undesirable locations under some instruction level parsing of the potential addressees. Something similar like this can also be incorporated incidentally into move and the load instructions, which I have not done, and that I think can easily be incorporated. So again, this is the last piece. If in fact we don't find the I guess the destination to be either one of the two blocks of memory, up to 8,192 that is, then we simply generate a page fault here. So this sort of brings me to the end of a discussion here on the instruction repertoire of Vesp 3.0. There's obviously plenty more in Vesp 3.0K, the kernel version, and I think we'll just talk more about this also in connection with the homework assignment when I am back in class on Thursday. But as far as the class for April 8th, I think I'm going to stop here and just add that I will post the new homework problem on ENEE350 website, so you should actually check that at your earliest convenience. But the first order of business is to get this tape class put on my ENEE350 website so that you can all download it before class tomorrow. So until Thursday, everybody take care, and I'll see you in class on Thursday.